Hello again, folks, in 114. Today we're going to be covering section 12.4. And here's the calendar just to confirm. Let's see. You know what? Didn't even adjust it yet. Today is Wednesday, April 14th. So as per the schedule, we'll be covering 12.4. Good. I had to make a little note. I did 12.3. Good. Okay. The packet is looks like this. I made another diagram in the style of the former two. This is a summary, firstly, of different types of variation. And ultimately what that means is that they're different formulae and a description of those. We'll go through that. You can annotate if necessary. Let's see. Okay. Then there are some word problems that I swiped from an older resource that I had, so I like them better. I think they're more illustrative. One is for range and the other one is for standard deviation specifically. I made an Excel spreadsheet, and I'm going to have it available so you can keep it if you'd like. That will show you how to calculate standard deviation more or less brute force, right? Which is good to do at least the first time, because it'll give you a better feel for it. And these are the column headings, even outlined by your book. They had suggested doing this by hand. Anyhow, I will show you how you could arrive at it the hard way and then the easy way. Anyhow, that's a table you could use to collimate data. And then there are 3 examples that are from your actual book. Okay? Let's see, I think that's the last thing. Well, I did swipe the basic information from the book if you prefer this. Alright, it has the formulas too. Alright, so if you're following along, do print that, and we'll get rolling here. Alright, let me give you sort of an overview. Alright, where we're at, right? Decided to call this MAT-114 statistics. That is the name of chapter 12 anyhow, but what we've been doing to this point and where we're going. Section 12.1 is about basically gathering data. I mean, there's more to it than that. There's also terminology and what have you, but that's the basic gist of it. All right, methods. Methods for gathering data. All right, 12.2. This is fading out. Let's see if I could adjust the blinds here. There we go. 12.2 is for different types of graphs, so what you might call picturing data. And the last section that we had covered was 12.3, was types of averages. Right, mean, median, mode, and mid-range. Right. And also types of position, technically. Okay, now where we're at is section 12.4 naturally. And there's some symmetry here, which is the reason why I wanted to even go through this. We have something called types of variation. Which is, I think, a more intuitive term. Just beware, all right? Types of averages have a more sophisticated sounding phrase, all right? You could, instead of saying types of averages, you could say measures of central tendency. Remember that types of averages is something that give you a feel, more or less, for the center of data. So this is in keeping with that. Measures of central tendency, right? And there's a similar, more sophisticated way of saying, alluding to this, types of variation, you could say, measures of dispersion. Which implies what it is about, right? Dispersion as in spreading of something. Anyhow, just be aware of the slightly more sophisticated sounding phrases referring to variation and averages respectively. Right? A lot of times the instructions will be talking about that, and I don't want you to go, geez, I didn't mention this. It's the same thing, it's just by an alternative name. I think types of variation and types of averages are a little bit more straightforward. All right, but beware. Okay. Now let me fire up the projector here, and we'll get going with the other diagram. I did exactly what I always do, which is forget to plug in the projector. So, developing a reputation. Early senility. There you go. Let's just scoop that over. Okay. Let's see if we can get that as bright as possible. There's a good old home page here. And this is the diagram that is relevant. Okay. Don't be deceived. I purposely designed this to look something like the last two diagrams. Just because I felt it was, part of a set. At least I wish it were. What am I trying to do? I'm trying to blow it up here. Okay. Alright, now let me explain what I've done here. Types of variation again, types of dispersion. The alternative way of referring to this. I purposely put this little thought balloon up here, just to have, not to have to go flipping for what the formula is officially for mean, right? There's an analogy that I'm trying to develop here, all right? Now, what is our types of variation? They give you a feel, as things in statistics do, for how different sets of data are, or how spread apart the values are in the set of data. Right? So essentially, give a feel for how different or spread out something is. And you have these choices, right? In our book, you're only responsible for this type and this type. This type exists, and you really can't talk about standard deviation without also mentioning the variance, but you're not really going to be using this, just one of these two. All right, now, when to use range, for example. I would use it when the total distance is sufficient information. You try to see how far the lowest value and the highest value are, right? Just calculating a range is figuring out how far apart the data are, right? What the extreme is, all right? If that is sufficient, and or if the data seem to be evenly spread. Now, one thing about the range, and the reason why it's not the go-to method really of these two things, is that it is susceptible to outliers. So you would want to maybe apply this if you're for sure don't have outliers involved. All right, a suspicious, there's a calculation for outliers, which again is interestingly you're not responsible for, but a suspiciously small or suspiciously large piece of data compared to everything else. All right, will give you a little deceptive reading. All right, this is easiest to calculate naturally, all right, but the least reliable because of potential outliers. So, all right, how do you actually do it? I would bet you've probably seen it when you were in grammar school. All right, it's really just subtracting two things. Subtract the lowest value from the highest value. All right, as is good practice, you would ideally have your data set already organized from least to greatest. All right, but anyhow, you're going to subtract the lowest value from the highest, which means that you would have to, in theory, write the high value on the left side of the subtraction symbol and the low value on the right side. All right, this is the formula down here. All right, don't do it the other way, because if you do it, you're going to get a negative. It's not commutative. Now, here's again why I included that little thought balloon with the mean up at the top here. All right. Types of averages, the one that is relevant or good for analogies here is mean. Right? And this is the formula, right? It incorporates the Greek sigma, capital sigma, which is implying the operation of addition. So if you see sigma and then x, it means x plus x plus x, whatever you need to, up to x to the nth one. Okay? N is the cardinal number, essentially, the number of numbers. Now, over here, you see two different symbols as options. You see x bar, and you see mu. Right? Which is a Greek sort of stylized looking U. Right? I'm just exaggerating here. Mu is the label that would be attached to this formula if you were looking for the mean of a population. Right? More often than not, you're just simply looking for the mean of a sample. So you will see x bar more than you will see mu. However, that exists as a label, so beware. When it comes to standard deviation, there are similarly these two options for the standard deviation of a population. The formula will have a lowercase sigma. Ironically, it looks like an O rather than that sort of E shape. All right, or just a regular standard capital S, if you will, if we're looking for a sample. All right. If you've been messing around with the calculator at all right, you might remember that if you set your calculator to calculate even just the mean, all right, and you scroll across the menu options, all right, what we had seen last time was that there was an S followed by the letter X, all right, and then there is this symbol, which is kind of a stylized O, lowercase sigma with a little x after it. Again, that is implying that it's for a population or versus a sample. There's just a slight change in the formula aside from that label. What actually is the standard deviation? All right. If again variation is something that gives you a feel for how spread out the data is in this instance, all right, the standard deviation has to have a common point. All right. So it's a standard deviation that is the spread from the mean specifically, right? When you calculate this, you really do need to have the mean first, right? You can get some software or what have you, get calculated to do that for you, but that is the reference point, right? Rather than 0 being a reference point, you use the mean instead, okay? So just be aware of that. All right. Now, when to do this, or to try this. Let me erase a little gobbledygook here. All right. The standard deviation is useful when you want it more reliable. That is more reliable than the range. It's very unreliable, as a matter of fact. It's more reliable measure of spread, right? All right. Why? Because it's essentially, it's like mean, but it's an average of distances, right? It's an average of distances from a common point. The common point, as I mentioned, is the mean itself. So rather than having everything compared to 0, you're comparing everything to the middle, all right? The center, all right? in general, the greater the variability of your data set and its values, all right, the larger you will see as a standard deviation, the larger magnitude number you'll see, okay? So those things are proportionate, right? Variability and standard deviation, whatever the figure is, they're proportionate, all right? All right, now, this is a bit complicated if you were going to do it by hand. And we'll do that maybe one time, but just to get you a feel. These are the steps involved versus just subtracting, which is why a person might try to do this instead of this. You first calculate the mean to establish the reference point, right? And then, and this is where it gets arduous, you systematically, one by one, subtract each of the data values, either to or from the mean. So I have it arranged in this sense that you have a slightly smaller number here, right? Well, and this will produce maybe a positive or a negative, all right, depending upon the arrangement of these two figures. That's x bar, that's the mean. This is regular x, that's a regular value. In a formula, notice the way that it's written, right, like so. I probably should have done it the other way myself. But anyhow, you're going to systematically subtract each of the values involving it and the mean. Then you're going to square each of those differences, right? That's the summary that you see here, this chunk of the formula, right? Then you're going to add all the squares. That's why there's a capital sigma in front of this parentheses in this square. Then you're going to take that sum, right? And you're going to divide either by one of two things. This is a bit subtle, but I put it as n minus 1 in parentheses, or a red n, right? Why blue, why red? Because again, if you're calculating the standard deviation of a sample, all right, it's not the whole population, so you would have to have at least one number lower, right? If you are calculating the standard deviation from a population, then you just use the cardinal number n, how many numbers of numbers there are. Okay, and then finally, you take the square root of this quotient, right? This is essentially the order of operations for calculating the standard deviation, summarized by this formula. All right, S is for standard deviation, capital S, right? It equals the square root of the sum of the differences squared divided by the sample. And again, it can get a little tedious because you'd have to subtract each of the values from the mean somehow. So if you have a large data set, you might be there a while, and that's why people tend not to do this by hand anymore. Right? They use a machine, right, or a calculator. Okay. Now, as I mentioned, you're not really responsible for variance, but literally variance is one step away from being standard deviation. Right? So just for comparison's sake here, right? When would you use this? When you're comparing sets of data, right? You want to see how far one is spread compared to another, how stretched out it is, if you will, the data values. You compare things that have some similarity, mind you. So what's the similarity? You compare sets of data in general with a similar mean, okay? And you don't care about the units in that case, right? Why? What actually happens is this. Actually, this is one step away from the standard deviation, the variance, all right? But the units do not match the units of data. How come? Because if the unit in the case of a standard deviation is just, say, hypothetically, inches is the outcome, the variance, because of the operations involved, would be whatever the unit is squared. So if you had inches, you'd have just inches as it returns to that. Variance is the unit squared. So they're not the same unit anymore, technically. All right? All right. This is the abbreviation for the formula. Variance is essentially the standard deviation squared. Right? Another way of looking at it, I suppose, is that it's really just everything that is underneath the radical symbol here. All right, that's the variance. All right. It's sort of undoing that. All right. Okay. So, again, of these three, the best choice really is standard deviation because of the continuity with the units. And again, it's basically it's an average of how far the data values are from some common point. And that common point is the mean. All right. So let's do some examples here. And to that end, I have this adorable picture of dogs here. All right. That's a little faded, but I like this problem because I made it as a worksheet a while ago. And it gives you a sort of a genuine feeling for what variation really is. This is the worksheet portion of it. We'll fill this in together. All right. All right. Now, what's the objective here? To illustrate measures of variation, and we're going to calculate a range. All right, and a mean in this case. All right. Now, just purely superficial. All right. If you were to compare this group of dogs, there's just 4 of them, of course. All right. And this group of dogs, right, which would you say has more variation, difference between one dog and another? All right. I would say that this has a greater variation. Probably greater variability. All right. Why do I say that? Because although it is not always good to just compare things by their size. All right, some things could be very large but deceptively light. You know, for example, they may not have as much mass, you know, but they have a large volume. All right, these dogs, being that they're all dogs, they're all, you know, of similar structure. All right, so it's a fair comparison. These are all very tall breeds of dogs. All right, if I had to hazard a guess, this looks like an Irish setter. This is like some kind of like Weimar or Weimaranean, something like that. I forget exactly. This looks like an American bulldog, and that kind of looks like a collie to me of some sort. All right. I love this one in particular because this is a Bernese. I used to have a Bernese, Pocono, his name was. He was a wonderful person. All right. But here you have next to him a Scottish Terrier, a little tot of a dog here. And then it looks like a Husky, Basset Hounds, and it's very faint. I'm not sure what this guy is over here. This is a Golden Retriever, a Dalmatian, and a British Bulldog. All right. Anyhow, you could see that there's a very low mass dog here, right? And a very large mass dog here. The Bernese Mountain Dogs are quite big, at least they can get very big, right? Anyhow, if now, having gotten through that, you look at the actual figures here. The set of weights of measured in pounds for these 4 dogs are 70 pounds, 73 pounds, 58 pounds, and 60 pounds, right? And in this set of 8 dogs, all right, you see that there are some very lightweight dogs. Probably the Scottish Terrier or the Basset Hound would be the lightest one, I would guess. All right, so you see like 30 pounds, 40 pounds versus 125. You know. Let us calculate the mean first of each of these. All right. So I left a little space here. And I'll leave the numbers visible. All right. The mean would be just a sample. So we use x bar is equal to the sum of these dog weights over the cardinal number. All right. In order, just to be a good little math geek. All right. Would be 58 plus 60 plus 70 plus 73. All right. Over 1, 2, 3, 4 elements. All right. What you should get when you add 58 to 60 to 70 to 73 is 261, I believe. All right. You can verify that. All right. And then what you'll see is that you don't get a whole number as a mean. You get a terminating decimal. So it should be 65.25, I believe. All right. save this figure. All right, keep it in that box. Now, just because I'm always skeptical, all right, I'm going to check it here. 58 plus 60 plus 70 plus 73. 261 divided by 4. Good. All right. All right. Now this one a little bit more tedious. All right. I'm going to do this in blue. All right. Same formula. X bar is equal to the sum of the x's over n. And we're going to do this. Let's see. The lowest number is, in theory, 30. So just to be a good guy and set a good example here, I'm going to put them in order. 40. And that looks like 42. And then 55. And then 60. And then 75. And then 85. And then 125. And there are, again, 1, 2, 3, 4, 5, 6, 7, 8 of these dogs in this set. All right. If you were to add all of these, what you should get as the sum on top here is 512. All right. Let me just confirm this because I'm suspicious. 30 plus 40 plus 42 plus 55 plus 60 plus 75 plus 85 plus 125. Yep, 512 divided by 8. In this case, you get a nice whole number. So the average here is 64 pounds. Save that piece of information. Now, what is important is if you were going to make any comparison now, it is a fair comparison because you have not exactly the same, unfortunately, but you have similar mean. They're not drastically different from one another. This is 65 and a quarter, all right, and this is 64. So pretty close for two different sets of data. All right. Now, just to get our feet wet here in terms of the idea of what has a greater variability. All right, not a super precise one perhaps, but something that's reasonable. Let us calculate the ranges of each of these. All right. And since I did take the time to put these in order, I'm going to borrow this number and this number when I calculate the range. The range is the highest value minus the lowest value. Okay, in this case it is 73 is the heftiest dog and 58 is the lightest. All right, so what is the difference between those? 5. Looks like it's 15. Our range is 15 pounds. Between the lightest and the heaviest dog, there's 15 pounds difference. Okay. Over here, again, I took the time to organize this, so good. We're going to borrow 125 and 30. So the high number is 125, the low dog is 30. And the difference between these is 95. A 95-pound difference between the heaviest dog, which is arguably the Bernese in the picture, and perhaps the Scottish Terrier, right? So, just a rough guess, right? Which of these, based upon ranges only, all right, would you guess has a greater variability? Well, the figures don't lie, they imply, right? This confirms our suspicion. Our guess. All right, this has greater variability. All right, we had a picture only to sort of make that estimate. All right, but now we have some actual numbers. All right, consistently applied formulae. All right, to validate that suspicion that the 8 dogs set has greater variability than the 4 dogs set. Okay, one should, again, you have to, if you've ever taken a philosophy class, one thing you learn from that is that you can't always trust your eyes, right? Indeed, if you're taking a chemistry class or a physics class, this is also confirmed, all right? Sometimes things that are very massive, right, are hollow, you know, so rather, I should say, things that are large in their volume are hollow, so they're not massive, really. They don't have as much matter to them, right? They're not as dense. Right. So be careful what assertions you make superficially, right? In the case of these dogs, it is a fair assertion only for the reason that you know what dogs are, right? You've seen them in your life, whether you've had them in your life or not. You know, it's part of your house. All right. All right. Now, the standard deviation example. Also swiped from another book, and I made a little table to illustrate. Looks like this. All right. This is, again, to calculate a standard deviation really is all that we're going to be doing. So that's all you're responsible for. Is to illustrate this example, we have the set of heights measured in inches of the top 6 players of the Cleveland Cavaliers in the 2011-2012 season. All right, so 75 inches tall, 81 inches tall, 83 inches tall, 78, 81, and 74. All right, as with any good statistics, all right, the easiest thing to get started is to put them in numerical order, rank them. So you might do that. All right, in which case, what would you get? That's easy. What's the low number? 74, 75, 78, 81, 81, and 83. Not too arduous a task because there's only 5 of these, pardon me, 6 of these players here. All right. Now, this is an outline if you were going to do it by hand again. Sorry, choking. All right, you would write them in numerical order. I kind of like fudged it because I put it in the wrong place. But I'm just going to replicate it here and then continue. All right. What you're going to see happen is you calculate the mean as you naturally would, all right, from adding all of these. And I didn't leave you a lot of space, unfortunately. I hope you will forgive me for that. But I'm actually not going to continue with this because I want to show you how to do this more efficiently, first with Excel and then with your calculator, or vice versa. All right, 6 is what you would divide by. What you should get from adding 74 to 75, 78, 81, 81, 83 is 472, which if you divide by 6 gives you, unfortunately, a repeating decimal. So I'm going to write this here in red just to make it stand out. 78.6 repeating, right, is the exact answer, all right? Which makes the arithmetic that follows a little bit more cumbersome. What it means is that if you have a repeater, you really end up having to round, all right, if you're doing this step by step, all right, and that could be problematic. This is why software would be a better course of action, because you will get a better answer, all right? Now, what the book had suggested, and I included this as a page, just to remind you, it's in the back here, is that if you're going to do this by hand, all right, and I would do it just one time by hand to get your feet wet, is that you write 3 columns. You have the data listed in order, and then you have the data minus the mean. You do those individual calculations and you write them in that column. And then you square each of the outcomes here. But rather than do that now, right, I made you, as I mentioned, this spreadsheet. Right. So let me show you this. Right. This is a blank spreadsheet. And you could, if you want to, start to fill this in. Right. If you put it in order, then in the spreadsheet here that you would end up typing later is that you would type 74, 75, 78, 81, 81, and 83 in this column, right? And then you can systematically tell Excel to take this data and write the mean here firstly, then apply all of those points individually to that mean, and then calculate that, and you will have another 6 values here. And then tell it to square that so that you can illustrate what's going on here. I think that would be a better use of our time, so I'm going to show you how to use that. All right? And as a matter of fact, I'm going to purposely put it out of whack, because one of the benefits of Excel is that you can get it to sort for you. Right? So you could write this down again if you want to follow along, but let me show you the spreadsheet that I also have available for you. Okay, this is Microsoft Excel. All right, and I'm going to purposely zoom in on this just a wee bit. No. No, I think that would be the reason why. Good. Just zoom in just a wee bit. Not to get distracted. As you can see, I already did this. I'm going to erase a lot of my work just to show you how this unfolds, piece by piece. Okay, there's a second copy of this diagram adjacent here, so you don't have to worry about this. What is relevant is basically the information from here to here. Right, I hope that the sun is not bleeding out too much here, but let us say that you entered your data in this first column, all right, willy-nilly, right? That is, you took the data that you had from the set that was disorganized, and you just typed it in the sequence that you see it here: 75 first, 81 second, 83 third. Right? Nothing wrong with that when you're using Excel, because it will rectify for you. All right. So what I'm going to do is just to illustrate, and I hope that this is close enough. Let me see if I can move up a little bit. That looks good. All right. In this column over here, where I'm establishing the data value column, if you will, X. Alright, I'm going to just type those values. So I'm going to type them out of whack. Here's 75, and it's defaulting to right justified on this edge. Alright, numbers are always like that, at least that's the way I prefer them. Alright, next one, 81. Alright, and you go down. It's a little tedious, alright, but it's just to get you used to it. Alright, 83, and then 78. Alright. And then 81 again, and then 74, right? And we have our 6 values. I took the liberty ahead of time of having it arranged here so that you see this is data value 1, 2, 3, 4, 5, 6, right? And in theory, if you had more data values, you would continue in this fashion. Now, what can you do? If it's out of whack, there is a feature in Excel somewhere in the toolbar that looks like this. It's a little A and a little Z and an arrow pointing down. If you highlight this, these cells from here to here, and then press that button wherever it is located, all right, in this incarnation of Excel, all right, it will automatically reorder them. It will put them in the order from least to greatest. Okay. In theory, you can have it switch the other way as well, but let me go look for it. All right. My version of it over here looks like a funnel, right, rather than an arrow. But I think traditionally it's more or less an arrow. And there's a little menu option that seems to exist. All right. You could sort A to Z or vice versa, Z to A, or you can have some kind of custom sorting. I'm just going to go with A to Z. All right. And I didn't even highlight it, and it already fixed it. All right. This version of Excel is for Mac that I have. So, and it's pretty up to date, so I didn't even have to highlight it to get it to do that. If you had an older version of Excel, you may have to be a little bit more deliberate. All right. Anyhow, if you wanted to calculate the mean and nothing else, what is true about Excel is that it is essentially a glorified calculator, a very powerful calculator, because you have the processor of the computer to do your calculations, and not just whatever processor could fit into a handheld calculator. This is great, don't get me wrong, it's even more powerful than, they say, the computer that took the astronauts to the moon. All right, but this is even more powerful than that. So every one of these cells you could operate as an individual calculator if you wanted to. And in this instance, just to dissect the process of calculating, I'm going to do that. It isn't really efficient, but it will give you, I think, a better feel for what's going on here. So I'm going to now take these data values and then calculate a mean, and the mean will be displayed right here. That's why I graded this out. All right. How do you get it to work? Well, you do the opposite of what you do with a calculator. Normally when you have a calculator, what do? You type whatever you have to, and then you press equals last, right? When you're using Excel, you do that exactly backwards. You press equals first to alert the software, essentially, that you're doing a calculation and you're not just writing a label. As you see, the headings here are labels, right? Those are words rather than, an actual calculation, right? So there's a couple of different formulas that are good to know, right? For example, if you wanted to calculate the mean, you could go digging through one of the menu options here is for function formulas, right? There's usually a button that looks like this somewhere, and it'll show you a list, but this one is specifically for the mean. You would write the word average all in capital letters, and then leave an open parentheses. So I'm going to type equals and then average, and now it's kind of like the board game Battleship. You need the coordinates in here to tell it where it wants to take data from. So I'm just going to highlight these, and what you're going to see is the coordinates basically of the first cell and the last cell, and a colon in between them to indicate from here to here. So you would have this from here to here. See, it says B4 to B9. Think of Battleship, right? There's B4, this column and this row, and this is B9. The colon in between is just indicating that you're stretching from here to here. What you have to remember, just to avoid a syntax error, is to close the parentheses, right? All right, and then you could just hit enter, and it tells you what the average is. 78.666 repeating, right? And it's rounding the number on the end, right? If you want to stretch out more decimals, you can. There's a feature up here. It's hard to see because of the projection, but I want to say it's this button or this button. That'll give you more, a greater precision. There'll be more decimal places. You'd have to highlight it first. Here's what I mean. See how it gets a little bit longer? Or if you went the other way, you can get it to just look like so, in which case it would round to 79. All right. Now, since the activity here is to, in theory, do this piecemeal, not necessarily by hand, I'm using software, but to do it in pieces rather than to go straight for the standard deviation, which is another one of these functions. All right, this is to illustrate what will happen if you now take the you take the mean and you involve 74, 75, 78, 81, 81, and 83 with it. All right, so what am I going to do? All right, I'm basically going to hit equals, all right, and now I'm going to take, I'm going to put a little parentheses, these values, right, and I'm going to hit minus, and then I'm going to type the location of the mean here, or I could just highlight it and it will automatically register. C4 is the location of the mean, all right, and what you'll see is that you get a negative, all right. You get specifically from having subtracted these two, 74 in front and then 78 after it, because that's really how it would work. All right, you will get a negative, in fact, in this instance. All right, so negative 4.6 repeating. All right, why? Because the mean itself was a repeating figure, and this is high precision. This is another reason why you like the software. All right, you get a more accurate answer. All right, so you don't have to keep typing this either. Now, if you just left-click this, you'll notice that there's a little box here in the corner. If you take that and you sort of left-click, hold down the left-click, and then drag down to where you are parallel to the bottom of 83 here. All right, you're adjacent to 83. All right. It'll automatically do those other calculations, at least it's supposed to. I must have fudged something, so let me erase this. Oh, there is one thing that I have to do, and this is a good time to explain it. There's a way of writing in Excel that you want more or less for the software to freeze a value in place, for lack of a better phrase. So like the location of this outcome for the mean is C4, all right? If I want Excel to just keep using this particular value and not automatically try to borrow from the number that is just underneath it, and that's basically what happened here, 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 and here just a moment ago, it automatically scooted down when it tried to make the calculation here, all right? The way that you get it more or less to freeze this as the place where you're drawing the mean from, for the sake of doing this subtraction, is you put a $sign in front of the coordinates. All right? So I have to go back to my original one here, and if you notice up in the heading over here, that what is the actual instruction to the function is exactly what got highlighted. So C4 is this. I just have to put the cursor here and put a $sign in front of C and in front of 4 as well. So I'm going to go up here. I'm sorry it's so blurry, but I'm going to put a little parentheses because I'm being anal, right? And $sign, skip $sign, and then close the parentheses. And there you have the same value. But now when I drag this, I'm going to, again, left click and hold it down so that I am adjacent to 83. And you see that it does all the calculations. If you clicked on any one of these individual cells and then analyzed how the software is handling it, you'll notice that what doesn't change, because I put a $sign in front of the coordinates, is that it keeps taking the mean from this location and not automatically from underneath it. Right? That's very important, okay? I miffed it because I forgot to do that initially, but I'm glad that it came up, quite frankly. Anyhow, again, you can, if you want to, take these and scoot them over like that, right? And you see that you get a greater degree of precision, right? Or if you go back this way, it automatically rounds everything, right? I think it would be better to leave it like that for right now, okay? Now, the next step that would be in the order of operations would be, okay, you've calculated the mean, you've done all the subtraction, right, is to now square it. You might wonder, well, why are we even squaring anything to begin with, right? remember what the standard deviation is basically. It is an average, right, of sorts. It's an average of distances of each one of these values from that common point. Unique in this problem, it's 78.6 repeating, all right? But what does that result in? Because of the lack of a commutative property in the case of subtraction, you get negatives in some instances and positives in others. What would end up happening if you were to do this again by hand, right, you would notice it maybe a little bit more obviously, is that rather than make things amplify from, remember part of the formula for calculating an average is to add, right? If you have a combination of negatives and positives in your addends, right, things that you're adding up to make a sum, they're not going to amplify, they're going to cancel out. So the way around that issue, even temporarily, is to square these values, all of them consistently. The key, remember how, I think I said this to you guys a lot, you can get away with murder in math, right? As long as you're consistent. If you've decided that you can't have a negative because there's going to be a cancellation effect as a result of trying to add negatives, as long as you square this, and this, that is the whole slew of them, everything is fair and square, haha. Alright? So, to expedite that, we're going to get the software to now do that work for us. Alright? And here's how you could do that again in brute force. Alright? You go to this column here, and you hit equals to start with, right? And since we're just squaring the differences, what I'm going to do is I'm going to put a parentheses to isolate, and then I'm going to highlight all of these. That is, D4 to D9 is the location of this number through this number. Close the parentheses, and then put the caret symbol in to raise it to an exponent, and then put 2, right? This is very brute force, but it illustrates what's going on here. Piecemeal, slowly but surely, right? And now hit enter, and now you see that's what the sum of the squares would be. Well, that would be the square for the first one. 4.6 repeating squared is 21.7 apparently. I'm going to again grab the corner and then drag this down to here since we have 6 points of data. And you see how squaring affects each of these differences independently of one another, right? The 81s produce the same difference of 2.3. These are positive. How come? Because their values are larger than the mean. 74 and 75 and 78 are smaller than the mean, which is why their differences produce a negative in this arrangement. Right? So, and 83 is 4.3. All right. Now, when you square them, thankfully, you no longer have a negative, right? But you've gotten a much larger figure, right? 3.6, instead of it being negative, is now 13.4. A positive, though. Negative 0.2 thirds, all right, is now positive 0.4 repeating, all right? And so forth, all right? 5.4, 5.4, all right? If you're a little suspicious of these numbers, remember, you can always try this with your calculator, all right, as you're going about it. All right, now, still inching closer and closer to the actual standard deviation, all right? We're going to now follow the instruction, the order of operations, and we're going to add all of these sums, right? Which is why there's only one space for these rather than 6 spaces and 6 spaces. The reason, again, why I grade this out is because you only have one mean, right? And you're only going to have one sum of squares, right? So to do that, you could just simply type equals and then try another function, right? In this case, the function that you would use is just the sum, right? So deep buried in the recesses of the function options of Excel, there is the sum function, which is just adding stuff. And again, it's in the style of a function, so you see a parentheses, and then you write the coordinates here, or you highlight, right? So I'm going to type sum, capital letters, parentheses, and then highlight from here to here, all right? And then close the parentheses, that's not it, and then hit enter, All right, so it's going to add the data that is located at E4 to E9. All right, and there you have it, 65.3 repeating. Okay? All right. Now, if we were just calculating the variance, right, we could just stop at this point. That is, we're going to divide by the sample. All right? How many data values? Minus 1. All right? So, maybe I'll scoot over just a wee bit here. And in here, I'm going to do that. I'm going to have to be a little crafty with my parentheses. All right, but you see what will happen. I'm going to divide the sum that is in this cell F4. Division is the / in Excel. All right, so / after the location of the sum here. And then I'm going to use another parentheses. And then you could type just what the number of values is. In this case, it would just be 5. All right, because if it is 6 data values, all right, minus 1, then it's a 5 here. All right. There's if you had a larger set of data, there is probably a way, I've forgotten it offhand, to borrow a function that will automatically decide, well, how many data values there are for you. All right, and then subtract 1. But I happen to know that it's 5, so I'm just going to use more or less a shortcut here. All right, all right. This number that you see, 13.06 repeating, is the variance technically. All right. If you go one step further and take a square root, all right, of this value, you will have the full-blown standard deviation here. All right. Now you notice that there's a figure here already. All right. That's because I forgot to erase that. If you wanted to calculate this value here, all right, what you're going to do is you're going to take 13.06 repeating and you perform a square root. So the function that you have available to you for the purpose of just square root is squirt, right? SQRT. Okay. So I'm going to type in here equals SQRT, squirt for square root, and then the location of the variance technically, which is G4, and then you close the parentheses to be a good sport, and you hit enter, and there you see it is. It's 3.6, right? The standard deviation is in the original units, which means that this is 3.6 inches, right? More or less the average distance, if you will, from the mean to the data. All right? One standard deviation, if you will, right, is 3.6 inches. If you had 2 standard deviations, it would be 7.2. If you had 3 standard deviations, it would be whatever that is. All right? 10.8, I think, right? Anyhow, this is, again, the most brute force way to use it, but it's giving you a high degree of precision, all right, and therefore a more accurate result here. If you want to skip over all of the minutia that we just went through, and I wouldn't blame you, all right, then there is already the function for standard deviation in your software here. So this is the function, all right? I believe it is just stdev, all right? And we'll see. I'll write it underneath it, and you'll see if we get the same number, 3.6. All right, stdev, standard deviation function. All right. So, right under here in this void here, I'm going to type that, stdev, and highlight the data that is here, 74 through 83. All right. Close the parentheses, the function. All right, and we'll see if it produces the same result, which we did the hard way, is 3.6. And there you have it. It's 3.6. All right. This is just to illustrate the step-by-step process that would be involved if you were doing it by hand and avoiding any issue where there's a round-off error in between. Remember, if you're doing a calculation, you generally do not want to round until dead last, all right? If you have software, you can more or less avoid that issue, all right, by stretching out your values here. Watch what happens if I go back to any one of these columns and adjust them like this. Like if I went back to here, to the original mean, and then reduced it to less decimal places, right? It will round this individual value, but the standard deviation looks like it's intact here, right? What about this column here? Anything that is dependent upon it might change, right? Well, it looks like the software is basically rectifying for us, which is great. Okay. Now, the beauty of Excel is this. Aside from being a glorified turbocharged calculator on steroids, is that once you have it established how you want it to operate, all right, you can go back to the original data values and start to enter more of them if you need to, or change them if you need to. If I threw in another figure in here, let's just say instead of 74, I put 94, all right, it'll automatically adjust that in the calculation. So let's say that you have a 94-inch basketball player, which is rare, all right, the standard deviation would change to 6.5, all right? In other words, it spares you from having to go through all that minutia, right? Right. Anyhow, this is kind of a cool thing, I think, which is why I'm mentioning it to you. Are you really going to do this every single time? No. All right. What you're probably going to do instead is you're going to use your calculator. So to show you, all right, the same problem with your calculator, all right, let's go through this exercise very quickly. All right. Here you have your TI-30, the requirement of this course. Turn it on. And remember, we got to clear the data that's in here. So you're going to hit second and then data, and then scroll over to clear data and hit enter. And then you're going to set it up to do one variable statistics. So you're going to hit second and then data again, and it's the first option. So hit enter. Now you're going to press the data button, and you're going to enter the values 74, 75, 78, 81, 81, and 83. All right. So I'm going to type 74, scroll down. There's just only one occurrence of this, so we're going to skip over frequency. 75, all right, scroll down. Again, there's only one occurrence of it. 78. 81, you could type it twice, but it would be practical in this case to type 81. And then when it gets to frequency, just type 2 instead. All right. And then this next one, you're going to put 83, right? Now you're going to go back to stat var here. And it will automatically tell you, all right, there's 6 points of data, all right, without having to type all 6 of them. We did 81 twice. There is the average mean already here. And then you see as your options, the standard deviation of the sample, which is what we want to compare to the value that is here, all right, and the standard deviation of the population, which would use the number 6 to divide rather than the number 5 in this case. All right, so I'm just going to scoot over here, and you see what it produces. A very high degree of precision, all right, of the same figure, 3.6. All right, when you are doing your work in my lab, use your calculator, all right, by all means, please, all right. It's pretty quick. You don't need to, run Microsoft Excel. But just be aware that this is a skill that is good to know, all right? And you can definitely handle it, all right? Think of this as being, the bazooka, all right? All right? And in order to handle large tasks dealing with large tables of data, you probably would want to use Excel. If you're doing something that's fairly limited, like you have 6 basketball players here, all right, use your calculator. So we'll move on now. Square right here, don't save. All right, you could take this off the spreadsheet that I have already rigged up if you like. All right, now to continue, let's go back to this sheet here. We'll do the textbook problems that you see here. There's an adequate amount of space, so we'll do that. That's too faint, sorry. All right. The amount of carbohydrates in grams of 10 different types of yogurt is given below. I notice it's out of whack, naturally. Determine the range of these data. It would be, again, setting a good example, and it's the only reason why I'll do it. All right. It would be setting a good example to put these in order, right? So, you have, let's see, the low number here is 8, and then there's a second one, 8, and then the next number is 9, and then there's a second instance of it here as well. And then after that, what do you have? You have, looks like 12 is the next one, and then 16, and then 18, and then 19, and then 26 and 29. Okay. So if you're going to calculate the range, as you well know at this point, it's just subtracting the high number minus the low number. And in this case, the high number is 29, and the low number is 8. Right? So therefore, the range is 21. Right? Grams. Right? What does that mean? It means that the distance from the lowest value to the largest value is 21 grams. Okay. Right. Right. This range is basically a distance. Right, between extremes. Okay, so there's quite a space, a gap, if you will, a variation from there to there. Right. Okay. Now, if you're going to calculate the standard deviation, right, again, I would use my calculator in this instance, so I'll do that now. A veterinarian in an animal hospital recorded the following lifespans of selected Labrador retrievers. Well, that's terrible. All right, to the nearest year. All right. Your calculator could probably handle this being out of whack, but again, I'm trying to set a good example here. This is not quite in order, so it'd be 7 first, and then 9, and then 11, and then 12. And then 15, and then 18. So not drastic. All right, but let us enter this into our calculator. All right. This is a worthy exercise. All right. So again, you want to clear out the data that was there. So hit second and then data. There was a sheet, incidentally, that I had made for you last class that explains this. Hit clear data. All right. Now make sure that you're in one variable statistics. Say yes. Second data, you want that. Now stat var. Alright, I didn't enter the data yet, sorry. Second, pardon me. Too much. Clear. Clear, thank you. Hit data button and now enter these figures. Right? You could do it out of whack, it will adjust, but 7, there's only one 7, there's only one 9, there's only one 11, there's only one 12. Remember to skip over frequency where necessary, which is all of them in this case. You don't want to accidentally put the figure where the frequency is, so just type where there's X's with subscripts. Okay. And you could always scroll up to verify that it is correct. All right, so the 6th data value, this is what the subscript indicates, is 18. The 5th is 15. All right, the 4th is 12. The 3rd is 11. The 2nd is 9. And then 7. Okay. 1, 2, 3, 4, 5, 6. All right, having entered all of those, all right, now you can hit stat var at this point, And it tells you that there's 6 data values naturally. This is the mean, 12. I'm reading it backwards. And we're after the standard deviation, so it's 4. Right. Remember, we want the, assume that you want the sample. So Sx is equal to 4. And what is the unit? All right. We're looking for the standard deviation of these Labrador lifespans to the nearest year. So the variation is, on average, 4 years from the mean. Okay. Next one, stock prices. All right. Determine the standard deviation of stock prices. I'm just going to enter this brute force. All right. Now it's just more or less an exercise in how well you could use a calculator. All right. And again, go back to erasing your data. So second data, scroll over to where it says clear, then put the data in. All right, it should assume that it's already in one variable statistics. So now you're going to enter systematically these values, right, without the dollar sign, of course. And you could put it in, it looks like it's in order anyway, thankfully. So it's just 17, 28, 32, 36, 50, 52, 66, 74, and 104 dollars. Okay, 9 stock values. All right, now you go to stat var. Tells you, confirms there's 9 values. Sorry for the blur. The mean would be $51 is the average, and the standard deviation is $57. Almost, if you round to the nearest penny, all right, would be where the 0 here is indicated. So $57, pardon me, $27.01. Sample standard deviation, about dollar sign in front, $27.01. Okay, if you round it. Okay, and that's it. Okay. If you're following along, all right, the schedule, all right, for homework, all right, do section 12.4 in my lab, and then you're right where you need to be. Okay, sorry for the faintness of that. Put that back. All right, I'll see you again on Monday. Be careful out there.